The next part of our discussion for the chapter on reactions in aqueous solutions, we will need to talk about several topics off this list, all in the same section of the chapter. We'll talk about which substances are acids or bases commonly, and give names to the common ones. Identify the ones that are known as strong acids and strong bases. Be sure we recognize them. We'll talk about polyprotic acids, and we will recognize acid-base neutralization reactions. Wow, that seems like a lot of topics for one section, but that's the way it works. There are a couple different definitions or theories of describing how acids occur and how we define them. And the one that's used here is called the Arrhenius definition, where a substance dissociates in water to produce hydrogen ions. So in a generic kind of sense, HA is an acid, and the hydrogen ion is produced in water to make an aqueous hydrogen ion that is combined with, or separating then from the anion A in solution. A more specific example is good old HCl, which seems familiar to many people, that when you put it in water, you seriously have no hydrogen attached to any chloride. It's aqueous ions, hydrogen ions, and chloride ions. However, the true nature of things, as shown in the diagram at the bottom, is when the HCl combines with water, you actually have hydronium ions instead. Hydronium is this H3O plus, is what results when you add a hydrogen ion to water. And so in a more true sense, the hydrogen ion does not occur by itself. It's too small. It truly attaches to water instead of just being by itself. So that's how we define an acid, those things which produce hydrogen ions or hydronium in solution. Then, what's a base? The next topic, or the next one then, would be the base. And the bases then are substances that dissociate in water, produce hydroxide ions. And so if one easy example or common example of bases are things that have a metal, M represents metal here, with hydroxide. Metal hydroxides dissociate to make a metal cation and a hydroxide anion, both of which are soluble. But if you remember the definitions, not all hydroxides are soluble. But those from group 1, such as sodium, are certainly soluble, and so they separate into aqueous ions quite nicely. Ammonia is another substance which is a base, other than the metal hydroxides. It's sometimes called ammonium hydroxide. It is weakly basic because it reacts to a small extent in water in an equilibrium fashion, actually. I should put a double arrow here to give some ammonium ions and hydroxide ions. And because of the presence of hydroxide ions, ammonia is also a base. So don't overlook ammonia. You will see that in your examples for bases relatively often. All right, here's another couple of things to think about. So we have some things that we should discuss. On the left is a bottle of ammonium hydroxide. Oh, well, you could also call it aqueous ammonia because it's literally ammonia in water that makes ammonium hydroxide. Fair enough. If you think about ammonium hydroxide, it sounds like it should be a salt, which it could be if you remove the water, but it's usually an aqueous solution. At the top, we see acetic acid. That's what's the compound that's present in vinegar, and it smells like vinegar. You would not miss it if you used it. It has one acidic hydrogen, and can you tell which one is the acidic hydrogen? The formula is CH3COOH, and the structure is shown there. And this is a case of the one that's different should be the one that's acidic, and it's in red here to give you the clue. So the ones that are the same, the three on the left, are non-acidic hydrogens. In other words, they do not dissociate from the molecule in producing an acid. And the one red one on the right side is the one that does dissociate to make an anion. So when you put acetic acid in water, it's going to dissociate, but it's going to be in equilibrium because it doesn't do this strongly, to make an acetate ion. And it's the CH3 stays intact, and the water picks up the dissociated proton to make, hydronium, H3O+. Now, let me fix that. We need to become familiar with the acids that are common and which ones are strong acids and strong bases are important to know. The strong acids, if you might have recalled from a previous discussion, are the 6 that are listed here. They're strong because they're strong electrolytes. They're not all 6 of them here. One is missing. HI is also on our list of strong acids. maybe it's not quite as strong as the others, but we'll list it with the strong acids. And their names are shown here: perchloric, HClO4, sulfuric, H2SO4, and hydrobromic, hydrochloric, and hydroiodic are the three from the halogen column. Hydroiodic have names that are very similar. And then the other one is nitric acid. Nitric acid is HNO3. You should know them. They are strong acids. There are only 6, and they are strong acids because they're strong electrolytes. Same thing is true for the strong bases. The strong bases are going to be things that are group 1 hydroxides, hydroxides of group 1 elements, things like sodium and potassium hydroxide. Also the group 2 hydroxides that are soluble, so things like barium and calcium. The lower part of group 2 hydroxides will be strong bases because, again, they're strong electrolytes. Weak acids and weak bases are the other ones. So any other acid you run into is going to be a weak acid, any other than those 6. And the bases are a variety of things. Ammonia is a weak base. It's not a strong base, but it is a weak base. And it's because it's in equilibrium. It's not complete dissociation. Remember that the strong and weak designation is completely connected to this notion of what kind of electrolytes they are. So strong electrolytes give you strong acids and bases. Weak electrolytes give you weak acids and bases. And so if you can't remember the formula for H2SO4, Willie was a chemist, but Willie is no more. What he thought was H2O was H2SO4. What is H2SO4? It is sulfuric acid. We hope Willie was only fictitious because one would not want to use that incorrectly. Okay, so we need to make sure we remember how to name these things. These 3 halogen acids, we need to know them. So HCl, HBr, and HF have proper names. They're hydrochloric, hydrobromic, hydrofluoric acids, and hydroiodic has the same pattern. That's how we name them. And there's a bunch of other acids that come from oxoanions. If you recall from our long list of anions, there's 2 anions with oxygen and nitrogen, nitrate and nitrite. They each have a corresponding acid. And so what we have to do is look for patterns here. When the anion has a name that ends in ITE, its corresponding acid ends in OUS. So the nitrite ion gives us the nitrous acid, and there we go, nitrous acid. And the nitrate ion gives us nitric acid. They're very similar in their charges and makeup, but they have distinct names and formulas. So 8s and ites, ix and 8s, oh brother. Wait, us and 8, yeah, if you have to stop and think about these, it makes us really easy to get tangled up, but try not to get them sorted wrong. So if you remember nitric and sulfuric has an 8 ending on its anion, and perchloric has an 8 ending over here. Chloric is the same idea, and chlorate ion goes with it. The other ones are the phosphate. I've missed that one, I forgot. The phosphate anion gives us phosphoric acid. The other ones that were ite anions are sulfite that gives us sulfurous acid, and hypochlorite, hypochlorous, chlorite, chlorus. So there's a whole set of acids with which you might become familiar slowly. How you recognize them is by remembering the patterns with the endings of the anions and their corresponding acids. Now, what in the world is polyprotic? Polyprotic is any acid that has more than 1 hydrogen that it can lose to solution. And so the polyprotic acids are going to be the ones that I'm going to mark with the green. Well, there's a few of them here. Sulfuric, sulfurous, and phosphoric of this list are polyprotic. So they have more than 1 ionizable hydrogen in their formula. Good things to know. All right, now let's talk about strong and weak in terms of picture diagrams. I know many people resist picture diagrams, but they're very helpful when you can sort them out. If the acid is HA, the little green sphere with a white knob on it, hydronium is red, oxygen with 3 whitish, grayish hydrogens on it, and the anion is the green. What is strong and what is weak? Well, remember, strong means complete or 100% mostly dissociation, and weak means only partial dissociation or very little dissociation. Partial dissociation when you put them in water. Which diagram represents which type of acid? So the strong acid has to be the one that's 100% dissociated. So the H and A, the hydrogen and anion, have to be completely separated. Well, only one of these diagrams should have that where the anions are completely separated, and that would be diagram number 2, where we have all hydronium ions and anions. So this is the strongest one. And then the weakest one is the one that's going to have the fewest dissociated anions from the acid. And I would assume from this example that we have 2 hydroniums on the right and 1 hydronium over here. So this one would be weaker, the weakest of these choices. All right, just examples that you can make up and think about them. Now, acid-base precipitation or acid-base neutralization reactions, be careful how I say that, are double replacement reactions where we swap the cation and anion pairs in the very same way that we did with precipitation reactions. So you have to think in terms of what component cations and anions are present in each of the reactants and then predict the products. So for a neutralization reaction, when you're done, if you've come out and done it in an equal proportion of acid and base or in a balanced equation fashion, there's no acid or base left because the products are going to be salt and water. And so in the case of the generic hydrogen HA acid with the metal hydroxide base, the H and A separate and the metal separates from the hydroxide, and the metal with the anion becomes a salt. The metal with the A from the acid becomes a salt, and the water comes from the hydrogen and the hydroxide. So this is not very tricky to figure out, but sometimes the balancing of the equations is more interesting if you have a multiple hydroxide base or a polyprotic acid. So let's try a couple of these. So we can write molecular ionic and net ionic equations for these reactions as well. And so we'll do one with hydrobromic acid, aqueous HBr, hydrobromic acid, and aqueous barium hydroxide. And to begin with, we always have to write the formulas of the products, predicting them carefully using proper rules for ionic compounds for salts. So don't forget your charges on things. We're going to use these again and again. Hydrogen ions +1 in this context. Bromide is -1. Barium is +2, which is why there's 2 hydroxides with it. And if you combine hydrogen with hydroxide, that makes water. And the barium with the bromide, you get BaBr2 because of the +2 charge on the barium. There you go. Acid plus base makes water and a salt. Next step is to write the molecular equation. So we're writing everything as though they're molecules, but we need to balance it as well. So we didn't do that on the previous slide, so let's do it here. So paying attention to pieces that are evident in the product, you had 2 bromines with the barium, so you have to put a 2 on the HBr. And you also have to account for where those 2 hydrogens go with 2 hydroxides. So that should make 2 water, because remember, hydrogen with hydroxide makes water. And so we put phases and predict the solubility, in other words, on the products. Water is always a liquid. Oh, that's not too surprising. But what do we know about barium bromide? Well, in this case, using solubility rules, bromide is going to be soluble because barium is not one of the cations that precipitates halogens. Silver, mercury, and lead are the notorious ones for halogens, and so it's not one of those. It will remain aqueous. We'll keep moving forward then and decide how else we're going to go from the molecular now to the ionic equation. In the ionic equation, we have to separate, dissociate as you wish, the strong acid and any soluble ionic compounds. Remember, strong acids are strong electrolytes and therefore also always listed as aqueous. Soluble ionic compounds are listed as aqueous, so we separate the ones that are aqueous. So 2 hydrogen bromide means you have 2 hydrogen ions and 2 bromide, both aqueous. Barium hydroxide is combining with this. Remember the balanced equation, we just had 1 of those. And so there's 1 barium ion and 2 hydroxide ions. If we do this right, it should all come out even. The products then give us 2 water molecules, which we do not separate. Do not separate, because it is not an aqueous ion. It is not an electrolyte. We are tempted to do that sometimes, but we shouldn't. It's just water. And then the barium bromide was soluble, so we separate that into barium ions and 2 bromide ions. That's the ionic equation. As before, these tend to be terribly tedious to write. Be careful about charges and subscripts and coefficients and phases. Lots of things to remember. The net ionic equation is the next step. Then what is where we figure out where the spectator ions are from the ionic equation, and we eliminate them to write the net ionic equation. The net is what the bottom line is, what the actual result is. So from the ionic equation, we can hopefully recognize what things are spectator ions. If you look at the left and the right side of the arrow, these are a little bit lined up too evenly for your purposes, perhaps. But the left side of the arrow, we see bromide ions that occur, the same as on the right side, and also barium ions. So we should be able to cross out bromide, that's a spectator, and the barium is also a spectator. Having removed those, we end up with the equation with 2 hydrogens, 2 hydroxides, and 2 water. Well, that's not the simplest form. We can get rid of all the 2's as coefficients. And the bottom line to the net equation for this acid-base neutralization process is that hydrogen combines with hydroxide to make water. This is very common as a net ionic equation for an acid-base reaction. Net ionic equation, I can't make my tool right, for acid-base neutralization when you have a hydroxide for a base and no other product. We could do another one, and we could figure out how this one works as well. The more practice, the better, right? Okay, so let's write the balanced ionic and net ionic equations for this reaction. First, we have to predict the products. So swapping the cation and anion, remember barium's +2, hydroxide's -1. Hydrogen, think of it as +1, sulfate's -2. So barium is going to combine with sulfate, 1 and 1. You've got to think about phases. And then the other product, oh, it's hydrogen with hydroxide. Well, guess what? There's 2 hydrogens and there's 2 hydroxides. That's a good clue that there's going to be 2 water. And we don't have to guess the phase on that one. Water's a liquid. Now, we have to predict what's happening with barium and sulfate. You've got to go back to your solubility rules, which once you get them down, you'll be more comfortable. It turns out that sulfates are commonly soluble, but not with barium. Barium, mercury, and lead. And so this one becomes a solid. Now, to write, that's the molecular equation. Now we need to write the ionic equation. Oh boy, these take a lot of patience, so be ready. So we'll separate all the aqueous substances into their component ions. So we have barium, +2 aqueous, 2 hydroxides, -1 ion that are aqueous, 2 hydrogen ions, aqueous, and 1 sulfate ion, aqueous. The products, then, we will separate the ones that are aqueous or strong electrolytes. Neither in this case. So we don't separate anything. Oh, well, that's a new example. Good reason to try out more examples. So we have barium sulfate and 2 water molecules as products. In this case, the net ionic equation has not changed anything. There are no spectators, which is sort of a surprise. You didn't know that was possible. No spectator ions because all species on the left show up in something that is either a solid or a molecular compound such as water. And so the ionic equation is the same or no different, no change as the net ionic equation in this case. So in spite of the fact that the formation of water from hydrogen and hydroxide is common for acid-base neutralization reactions with hydroxides as bases, not always. If you have a solid in your products, there won't necessarily be that simple of a net ionic equation. Okay, we're on a roll. Let's do some more. Let's do another one with aqueous sodium hydroxide, aqueous hydrogen fluoride. And so we write the chemical formulas of the products, predicting these things from proper ionic rules for formulas. And so we have HF aqueous and sodium hydroxide aqueous. There's your acid, there's your base. The products then become water and sodium fluoride. And we have to decide next, in the next step, in our molecular equation, we will balance it. So now we have to balance the equation and predict the solubility of the salt in the products. Using our solubility rules, we'll have to decide what to do with the sodium fluoride, etc. Well, sodium is always going to be soluble, so you don't have to worry about that. Sodium is always going to be aqueous, and water is still a liquid. So the equation needs to be balanced, but this was a +1, -1, +1, -1 cation, anion set, so we don't have any other coefficients to add in this case, so we got the molecular equation. Ready next for ionic. The ionic equation, remember we dissociate the soluble ionic compounds and any strong acids. And so to write the ionic equation, what do we have? We have HF, that's listed as aqueous, and we list the sodium hydroxide as aqueous, and separate the sodium from the hydroxide. We make water, which is a liquid, and then you have sodium ions and fluoride ions aqueous. Now, technically, this one comes out a little bit funny. This one's a little unusual because we don't, this is not an ionic compound. This is a molecular compound, and it's a weak acid. It is aqueous, that means it dissolves, and it's a molecular compound, not a soluble ionic compound. So it's a molecular compound with very little dissociation, honestly. And so we do not separate the ions here, unlike what we might have at first thought. So having done the ionic equation, now we can move forward to figure out what the net ionic equation should be. So we have to figure out what the spectator ions are from the ionic equation. And if we look at this ionic equation, what's a spectator here? Well, I would see that there is sodium on the left and sodium on the right. So sodium must be a spectator ion. Sodium is very commonly a spectator ion because it stays aqueous, most of your examples. And so we drop the sodium out of this equation, and the net equation, the net ionic equation, is this hydrogen fluoride combines with hydroxide to make water and fluoride ions. Seems kind of more interesting than you first would have guessed. All right, one more example for this recording. We have an opportunity to come up with a balanced net ionic and net ionic equation for the reaction of calcium hydroxide with acetic acid, which is the compound CH3CO2H. The more practice, the better. Okay, so predict the products to begin with. And remember the charges on the cations and anions, and you'll be pointed in the right direction. Oh, but this is cations and anions. Well, this is acetic acid, and so it has the possibility of being an acetate ion, which is the -1 anion, that part, and the hydrogen ion. So when you make products, the calcium has to combine with a different anion. So in this case, it's going to be acetate, but it's a -1 anion. So we put the formula together as CH3CO2, and -1 anion with calcium means there will be 2 of them. The other product then becomes hydrogen with hydroxide. Oh, we've seen that before. Hydrogen hydroxide is still our friend water, still a liquid. Balancing this, what do we have to do to balance it? Well, in order to have 2 acetate on the right, there better be 2 acetate on the left, and that gives you 2 hydrogen ions to go with 2 hydroxide ions, and 2 water molecules as a product. Okay, so we haven't written the ionic equation yet. Oh, so let's look at that and think what we'll have. So to write out the ionic equation, we'll have the calcium ions, aqueous, 2 hydroxide ions. Oh, I didn't need parentheses there. Take that out. 2 hydroxide ions are aqueous. Get carried away and leave them in when we don't need them. The aqueous gets a parenthesis. And then 2 of the acetic acid. This is going to feel funny because we didn't take this one apart just like the last example with hydrogen fluoride. It's not an ionic, it's a molecular compound. CO2H is aqueous. On the right, oh, we forgot to predict solubility on the right. Oh, we missed that step. So in order to do that, we need to know the solubility of calcium acetate. Acetate is one of those ions that is always soluble. And so that makes life easier. It's always soluble. And that means that the label should be aqueous. Forgot that step, sorry. Now, what do we do with the products? So the products, we're going to have soluble potassium acetate, or calcium acetate, say the right name. So calcium ions are still +2 and aqueous. There's going to be 2 of the acetate ions. So CH3CO2- are aqueous now. And then there's water. Water is still water. We don't take water apart. It is what it is. It is a liquid. Surprise. So now we want to decide what the net ionic equation is. What are the spectators? To come up with the net ionic equations. Then first we have to look and see what's the same left and right. Well, it looks to me if you start from the left side, you'll recognize that calcium is there twice. So calcium is one of them. And nothing else. Everything else has a change from left to right. The hydroxide goes from being aqueous to combining to make water, and the acetate goes from being in a molecule to being a separated ion. So what the net equation amounts to, so net equation, we have 2 hydroxides combining with 2 acetate ions. Oh, sorry, acetic acid, that's what that is. Acetic acid, CO2H, aqueous, to make 2 free acetate ions. They're aqueous now. And 2 water molecules. Well, guess what? This could be one step simpler, right? We can take out all the 2's, and we end up with hydroxide combines with, whoops, aqueous hydroxide, combines with acetic acid to make acetate ions. And, oh, I forgot to list aqueous. I told you there's lots of parts on these, huh? And the other product is water. All right, many examples, the more the merrier. I hope this helps you on your homework. I realize this was a long set of recording, but maybe you find it helpful. Please ask more questions. See you in class.